Welcome to this training module on NVIDIA Spectrum Networking with a specific focus on the transformative role of data processing units or DPUs. We will explore how Bluefield DPUs and Spectrum switches work in concert to accelerate modern data centers. Let's start by setting the stage. Traditional data centers relied heavily on the CPU for everything: applications, networking, and security. However, in the era of AI and big data, the CPU has become a bottleneck. We are witnessing a shift to a data-centric architecture where the data processing unit, or DPU, takes on the heavy lifting of infrastructure tasks. This allows the CPU to focus on applications and the GPU to focus on acceleration. Crucially, the network itself must evolve. NVIDIA Spectrum switches are not just passive pipes. They are designed to integrate tightly with Bluefield DPUs to deliver enhanced telemetry, congestion control, and performance isolation. So what did we learn? We learned that the DPU is the new critical processor for infrastructure, relieving the CPU and enabling a more efficient, accelerated network fabric. This flowchart compares the traditional model to the modern data-centric model. On the top path, you see how relying solely on the CPU leads to bottlenecks as network speeds increase. On the bottom path, we introduce the DPU. By offloading network functions to the DPU, we accelerate the entire system. The DPU then connects into the NVIDIA Spectrum fabric, ensuring that traffic flowing to your GPU and CPU clusters is optimized and efficient. Now, let's look closer at the Bluefield DPU itself. Think of it as a computer in front of a computer. It resides in the server but operates independently, running its own Linux OS on programmable ARM cores. It combines the power of NVIDIA ConnectX networking with specific hardware accelerators for encryption, storage, and packet processing. Why is this architecture important? It allows you to offload the entire infrastructure, stack, software-defined networking, security policies, and storage virtualization from the host CPU to the DPU. This not only saves CPU cycles but creates a clean separation between the infrastructure and the tenant workload. What is the important point here? The Bluefield DPU is a complete, independent infrastructure processor that isolates and accelerates networking functions. This diagram visualizes the structural relationship. The host system with its CPU and memory connects via PCIe to the Bluefield DPU. Notice how the DPU contains its own specialized components: the ConnectX adapter for connectivity, ARM cores for programmability, and accelerators for speed. The DPU then acts as the gateway to the external network and Spectrum switches, effectively shielding the host and handling all network traffic. This brings us to NVIDIA Spectrum X, a groundbreaking platform that perfectly illustrates the synergy between switch and DPU. Spectrum X combines the massive bandwidth of Spectrum 4 switches with the advanced capabilities of Bluefield 3 Super NICs. Traditional Ethernet was built for general compatibility, not the intense, synchronized bursts of AI traffic. Spectrum X changes that. It is purpose-built to supercharge generative AI clouds. By tightly coupling the switch and the DPU, we achieve up to 1.7 times better AI performance and energy efficiency. The DPU isn't just moving packets, it's participating in the fabric to ensure maximum throughput for AI jobs. What did we learn? We learned that Spectrum X leverages the DPU to transform standard Ethernet into a high-performance AI fabric. Here we see the core of the Spectrum X platform. The Spectrum 4 switch and the Bluefield 3 Super NIC are locked in a high-speed, synchronized link. This combination directly drives AI workload optimization and power efficiency. It is not just about the switch having high bandwidth, it is about the Super NIC intelligently utilizing that bandwidth to accelerate the specific needs of AI applications. One of the critical technical challenges in AI networking is handling massive data flows, often called elephant flows. In a standard network, these can cause congestion. With Spectrum X, the Spectrum 4 switch uses adaptive routing to spray packets across every available path, balancing the load perfectly. However, this means packets arrive out of order. This is where the DPU shines. The Bluefield DPU takes these out-of-order packets and reassembles them in the correct order at wire speed, transparently to the application. This allows the network to run at nearly 95% effective bandwidth. What is the important point? The DPU's ability to handle packet reordering allows the switch to fully utilize the network capacity through adaptive routing. This sequence diagram illustrates the data flow. The sender transmits a stream to the Spectrum 4 switch. The switch uses adaptive routing to spray packets across multiple paths. Consequently, packets arrive at the Bluefield 3 DPU out of order. The DPU internally reorders these packets and uses direct memory access (DMA) to write the ordered data directly to system memory. Crucially, as the note indicates, this entire complex process is transparent to the host CPU. Congestion is the enemy of AI performance. Spectrum networking tackles this with a sophisticated telemetry loop. The Spectrum 4 switch constantly monitors its buffers and sends real-time telemetry data to the endpoints. The Bluefield DPU receives this data and executes advanced congestion control algorithms. Because the DPU is an intelligent processor, it can react in microseconds, adjusting the rate at which data is injected into the network. This flow metering prevents congestion before it causes packet drops, which would otherwise stall expensive AI training jobs. What did we learn? We learned that the DPU acts as an intelligent traffic cop, using switch telemetry to proactively manage flow rates and maintain network health. This state diagram shows the control loop. The Spectrum 4 switch starts by monitoring its internal queues. It sends telemetry data indicating congestion levels to the Bluefield DPU. The DPU calculates the optimal transmission rate and then transitions to injecting metered traffic back into the switch. This tight loop ensures that the network operates at peak efficiency without becoming overwhelmed. In a modern AI cloud, multiple tenants share the same physical infrastructure. A common problem is the noisy neighbor, where one user's massive workload chokes the network for everyone else. NVIDIA Spectrum X uses the DPU to solve this through performance isolation. The DPU enforces strict quality of service QoS and traffic shaping policies at the edge. This ensures that every job gets its guaranteed bandwidth and latency, regardless of what other tenants are doing. This predictability is essential for cloud service providers offering SLAS to their customers. What is the important point? Bluefield DPUs enforce performance isolation at the server edge, ensuring fair and predictable network access for all tenants. Here we see a multi-tenant server hosting AI Job A and AI Job B. Both send traffic to the same DPU policy engine. The DPU isolates flow A from flow B before they even leave the server. When they reach the Spectrum switch, they are treated as distinct, protected flows, ensuring that both destination A and destination B receive their guaranteed bandwidth without interference. Security is paramount, but it often comes with a performance cost. Bluefield DPUs introduce a zero-trust architecture by decoupling security from the host. Security agents, firewalls, and encryption protocols run directly on the DPU's ARM cores, completely isolated from the host OS. This means that even if an attacker compromises the host, they cannot disable the security controls running on the DPU. Furthermore, the DPU offloads encryption tasks like IPsec and MACsec, protecting data and motion at full line rate without slowing down the application. What did we learn? We learned that DPUs provide a robust security boundary protecting the data center infrastructure even from compromised hosts. This diagram depicts the security boundary. The host domain contains the user app and host OS. Traffic leaving the host must pass through the DPU trust domain. Here, the DOCA Firefly firewall inspects traffic, and the IPsec engine encrypts it before it hits the network. This physically and logically separates security enforcement from the potentially vulnerable host environment. Finally, how do we unlock all this potential? The answer is NVIDIA DOCA. Just as CUDA revolutionized GPU programming, DOCA is the framework for programming Bluefield DPUs. It provides a unified set of drivers, libraries, and APIs that allow developers to easily access the DPU's hardware accelerators. Whether you are building a custom firewall using DOCA Flow or a storage application using DOCA Compress, DOCA abstracts the complexity of the hardware. This allows you to rapidly develop and deploy software-defined infrastructure applications. What is the key takeaway? DOCA is the key to unlocking the DPU's power, enabling flexible software-defined infrastructure on Bluefield. This diagram shows the DOCA software stack. At the top are user applications and services. These interact with the DOCA libraries and drivers layer. This layer communicates with the DOCA runtime and telemetry services, which ultimately control the underlying Bluefield hardware accelerators. This layered approach simplifies development while ensuring maximum performance.